This diagram outlines the harsh physics of ancient flight. For decades, researchers treated a 36-foot wingspan, like that of the famous Quetzalcoatlus, as the maximum threshold for biological flight. A 500-pound reptile attempting a two-legged avian takeoff would likely shatter its own skeleton under the weight of the jump. These giants utilized a quadrupedal launch to bypass those limits. By leaning forward, they loaded tension into their massive chest and wing muscles like a biological catapult. This allowed them to vault upward, clearing the ground in a single, violent motion before the wings ever took over. This structural balance of hollow bones and explosive power defined our understanding of the sky until the discovery of the Hatzeg Basin in modern-day Romania. Archaeologists uncover pterosaur remains featuring thick, reinforced bones and internal struts designed to withstand extreme physical impact. 66 million years ago, the map of Europe consisted of a scattered chain of tropical islands. One of these isolated landmasses, the Hatzeg Basin, functioned as a closed ecosystem where the standard rules of mainland survival no longer applied. When physical isolation removes the competition of a larger continent, evolutionary pressures diverge. On Hatzeg Island, these pressures produced specialized anatomy that contradicts the typical lightweight requirements of flight. This scale comparison illustrates insular dwarfism. On Hatzeg Island, the lack of space and vegetation meant massive 80-foot sauropods could not survive. Over generations, they adapted to the limited resources by shrinking until they were roughly the size of a modern pony. This reduction in prey size left a massive ecological vacuum. Because the island was isolated, it lacked the giant terrestrial carnivores found on the mainland. For millions of years, the role of the apex predator remained unfilled. The pterosaur Hatzegopteryx arrived to fill that void. It shifted away from the efficient soaring of its cousins, evolving into a 16-foot-tall ground predator that utilized its wings as massive walking limbs to stalk the island's plains. To hunt on the ground, the creature required specialized weaponry. This cross-section shows the Hatzegopteryx neck. It is 3 times wider than its relatives and reinforced with internal bone struts. This structure allowed it to drive a 10-foot rigid skull into small dinosaurs with the force of a sledgehammer. On Hatzeg Island, the sky became the primary source of terrestrial danger. The extreme isolation demonstrates how the anatomy of a flyer can be repurposed to dominate the ground when the apex predator role sits empty. While island life forced giants into miniature forms, the mainland offered the opposite extreme. With unlimited space and abundant vegetation, the physical boundaries of animal life were pushed toward a massive scale. In prehistoric South America, Argentinosaurus reached the absolute limits of terrestrial mass. At 100 feet long and weighing 100 tons, its sheer bulk provided a passive defense, making it largely immune to the predators of its era. Other mainland predators specialized in smaller, more agile prey. North America was home to Diodon, a massive mammal with a bone-crushing bite, while Australia was stalked by Megalania, a 680-kilogram lizard that utilized powerful claws to climb trees for ambush hunting. Some carnivores avoided the competition of the plains by moving toward the water's edge. Spinosaurus emerged as a dominant predator by bridging the gap between land-based hunting and aquatic environments. Spinosaurus utilized a narrow, elongated snout for snatching fish and webbed feet for propulsion. These adaptations allowed it to patrol coastal shallows, targeting aquatic prey rather than competing for the armored herbivores of the deep interior. These continental giants pushed the structural limits of bone and muscle against gravity. However, the most significant increases in scale occurred only where the downward pull of gravity was negated by the environment. In the deep ocean, the physical constraints of terrestrial life vanish. Buoyancy counteracts the weight of a massive frame, allowing predators to reach proportions that would collapse under their own mass on land. The 60-ton megalodon thrived in this gravity-free arena. By moving away from coastal prey, it sustained its massive size by hunting large marine mammals, including early species of whales. This tooth illustrates the mechanical efficiency of the megalodon. A bite force estimated between 10 and 18 tons allowed the Sherpa to shear through thick blubber and shatter the bone of its prey with a single strike. The megalodon shared these waters with Leviathan, a predatory whale with teeth measuring 36 centimeters. These are the largest carnivorous teeth of any known animal, designed for tearing into the flesh of other large marine mammals. The ancient oceans became a theater for an evolutionary race of pure mass. Without the limitations of land, these predators developed jaw strength and body sizes that remain impossible for any creature confined to the shore. When we compare every giant across all of Earth's history, from the armored Romanian flyers to the massive Miocene sharks, one creature clearly stands above the rest as the ultimate giant. The modern blue whale holds that crown. At 30 meters and 200 tons, it's significantly larger than any dinosaur or marine reptile ever discovered. To sustain this size, the whale utilizes specialized internal biology. This heart model, the size of a small car, pumps over 10,000 liters of blood with each beat to support its massive frame. The blue whale also produces the most powerful sounds in the animal kingdom. Its calls reach 188 decibels, a volume that exceeds the noise of a jet engine, allowing it to communicate across thousands of miles of ocean. The record for the largest animal to ever live is held by a species in our modern oceans. These 200-ton giants represent the current extreme of biological scale, and we hold the responsibility of ensuring they remain a part of the planet's future.